In July 2017, at the US National Governors Association meeting, Elon Musk told more than 30 state governors exactly how much land would be needed to power the entire country with solar energy.
You only need about 100 miles by 100 miles of solar panels to power the entire United States. And then the batteries you need to store that energy to make sure you have 24/7 power is 1 mile by 1 mile. One square mile. That's it.
He was speaking a bit hypothetically, of course. We all know the world isn't as simple as that, and the barriers to achieving that goal, even if it were set as a target, would be pretty mind-boggling, not least of which would be the storage interconnections to an old and failing grid, and of course the fierce and brutal opposition that any such proposal would face from the fossil fuel industry. But there's another potential hurdle that isn't quite so well understood, and that's the fact that by the very nature of the way existing solar panels are constructed, there's a physical limit to how much sunlight they can convert into electricity. That limit equates to about 30% efficiency, and in fact the most common solar panels used today actually only achieve a real-world efficiency of about 23%, and even that took about 40 years to achieve. The panels dear old Jimmy Carter had installed on the roof of the White House back in 1979 were barely more than 14% efficient. Unsurprisingly then, there's a huge global competition to discover and develop new and exciting ways to improve solar panel efficiency in an economically viable way. And one of the most promising new materials in development is something called perovskite. So what is perovskite and how will it help? Hello, and welcome to Just Have a Think. I mentioned that it was a new material, but actually perovskite was first discovered in the Ural Mountains in the early 19th century by a geologist called Lev Perovsky. Perovskite in the wild is a mineral made from calcium, titanium and oxygen. Rather than traipsing around the world digging up the naturally occurring mineral though, scientists have developed a whole class of materials called perovskite structures. They have the same crystalline cube and diamond-like shape as naturally occurring perovskite, but they can be synthesized from a fairly wide variety of commonly available and relatively cheap chemicals. The scientists refer to them as ABX3 structures, with A and B acting as cations and X acting as an anion. So how can perovskite structures help with solar panel efficiency? For a start off, unlike silicon solar cells, perovskites don't need that extra phonon to liberate the electrons from their middle layer, which means they can be manufactured as very thin films using a technique known as solutions processing. Perovskite structures are also much more tolerant to defects than silicon, and that eliminates the need for the high-cost, high-energy machinery that silicon cell production requires. And it also means about 20 times less material is needed for each cell, which in turn means a smaller environmental footprint from production. Perovskite cells don't use rare earths or any supply-limited materials, and they can be made into traditional rigid solar panels or flexible panels for more diverse markets like the leisure industry, and return on investment can be measured in months rather than years combination. So perovskite solar cells really do look like they offer the prize of an ultra-adaptable, ultra-thin, flexible, cheap, high-performance solar cell which could accelerate the move away from fossil fuels and perhaps a bit closer to Elon's 100 square mile analogy. There are already several companies all over the world that are racing to capture this potentially enormous market, including Oxford PV, a spin-off from Oxford University, co-founded by Professor Snaith himself. I'll leave the last word, though, to the author of the Solar World Power article, Dave Buimi of Prescient Energy Consulting, who reminds us that to meet 20% of all global energy for the UN's emissions reduction scenario, the solar industry would need to install between 300 and 500 gigawatts annually over the next 30 years. Current global PV module manufacturing at 100 gigawatts per year already presents an enormous supply chain challenge. Perovskite solar, with its unique simplified manufacturing attributes, raw material, performance and small environmental footprint, makes it highly scalable quickly. Depending on the business model, perovskite modules can be manufactured in facilities that cost 50% less than other solar factories and use less material. The supply chain to support manufacturing is also small, allowing for factories to be sited close to end markets. The perovskite solar cell industry is in a state where its lab developments already exceed prior solar panel commercialisation launch points. As with all these new technologies, the challenge, of course, is how quickly the simplified manufacturing can scale up for a given production method to enter high volume production.